All right, welcome back. So, what we're going to do is we're going to talk about how to apply the ideas we've been talking about to sort of a little bit more practical uh, way of using them. Um, and what I'm talking about is that in the last few sections, we've been using this idea of the law of large numbers or the central limit theorem to talk about how if we take a sample that's large enough, we can just assume that the population parameter, like the population mean, is equal to the sample mean, or the population proportion is equal to the sample proportion. So that's kind of just like an assumption we've been making, that we can just sort of say, oh, well, we'll just assume that the averages are equal. That's not really what we would see in a practical setting. For example, if we wanted to know, and this is in section 9.1 in the book, which I've posted, and I'm just going to kind of read through this first little idea here, how to obtain a point estimate. So suppose we wanted to find an estimate of the proportion of adult Americans who believe the amount they pay in federal income taxes is too high, right? Okay, so there's too many people. We're not going to do that. We're going to take a sample of people, and that's going to give us an estimate for the actual proportion, right? That's the whole idea of statistics. We're going to sample, and the proportion we get from the sample is going to be an estimate of the actual population proportion. So here's what we're going to do. We're going to talk about how to estimate the actual population proportion. So I'll just use P for that. So to estimate the actual population proportion, so that's the actual percentage of, in this case, Americans who believe the amount they pay in federal income taxes is too high, right? That's the actual percentage. It's right now it's unknown, right? So I'll just put that down. It's unknown. We sample and we obtain, or we get a point estimate and try to spell that right. And that's where we use p hat, right? This is our sample proportion, and it's just right the number of observations divided by our sample size. So this would be the number of observations or successful responses, however we want to determine that, and this would be our sample size. It's literally just saying, if you sample 1,016 Americans and 558 said yes, I believe it's too high, then 558 divided by 1,016. And that's the example one that they're showing there. So for example, the 558 divided by 1016 gives us 54.9%. And that's our p hat. Okay, so that's our estimated population proportion. We understand, though, that that's just from a sample, right? And if somebody else goes out and samples a different amount of people and different people altogether, we might get a different percentage, right? Maybe we get a percentage that's 56.3. Okay. The idea is that if we do this enough times, we would eventually be able to get to that actual population parameter. That's what we were talking about with the sample distribution, right? Sample distribution of proportions, because we're doing a bunch of samples. That's not really practical, though. What's practical is to do one sample. So the idea here is that we're going to do one sample, and this point estimate that we get is going to be our estimation, but we're not just going to say, okay, so 54.9% of people, because we're not sure. What we're going to do is we're going to give a little range, right? And that's what this confidence interval really is. We're going to give a range of values. We're going to give a spread of values. So let's see how we're going to do that. So here's a good little visual, right? We make a guess. We make a guess based on our population sample proportion. So we make a guess, and we're going to put a confidence level to that, of how confident we are that the actual population parameter is within the numbers we give, right? So if I wanted to be 100% confident, I could be 100% confident that I actually know this population proportion, right? I could say that I'm 100% confident that the percentage of Americans who believe their income tax is too high is between 0 and 100%, right? Like, you can't really argue with that, right? That isn't helpful, but I am 100% confident that it's between 0 and 100%, somewhere in there, right? That's the idea of a confidence level. I can be very confident if I have a very wide confidence interval. Okay? Again, that's not helpful in my example. What's more helpful is if we actually take this idea of the normal distribution curve and apply it to the population estimate. So here's what we're going to do. So first of all, let's take a look at the definitions. A confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate, right? So just like what I said, I'm 100% confident between 0 and 100. But let's say I actually want to come up with one that's reasonable to use. I could then say maybe I'm 90% confident that it's between 49 and 54%. Right, that's a little bit more reasonable. It's a little bit more useful to use, because then we're narrowing down the idea, right? So for their example, they obtained the 54.9%, and then they used a 95% confidence interval, which is a pretty standard confidence interval to use. So a 95% confidence interval, what that means is that 95% of all I'll just call these confidence intervals constructed will contain the actual population proportion. So remember, that was our goal, right? To estimate that actual population proportion. We don't know the actual percentage, but we're going to give a range, and 95% of all the confidence intervals constructed in this way will give us will contain that population proportion. So that means that you can take different samples, come up with different confidence intervals, but 95% of them will contain the actual population proportion. Okay, and that's what a confidence interval looks like. So this idea of, first of all, a 95% confidence interval, we kind of want to draw what that means. And that's kind of putting the 95% right in the middle, okay? And so we have to remember kind of what this area is and what this area is. And the book does use, for 95% confidence interval, they use a symbol, an alpha symbol. And they put alpha equals 0.05. And so they're talking about the percentage that's not inside the interval. But we have to remember that the 95% is in the middle. So this is actually 2.5% here and 2.5% here. Okay? So what we do is we find there's a little formula here that we're going to use, and that gives us the sort of standard margin of error, and what that's going to be, and it's the third bullet here on this next page, and that's going to be, so this is the standard margin of error, and square root of PQ over N, which might look familiar because we've kind of talked about that before in terms of the sample distribution. Okay, so that's for the standard error. To come up with the entire interval, what we do is we're going to add and subtract this sort of value from our point estimate. So the book goes into all this different stuff. Let me give you the formula here. So what we're going to do is, let's just put our formula here. And it's going to be p hat. So that's going to be the point estimate we obtain. And then it's going to be plus and minus. So there's going to be two different computations to do. And then it's going to be a z-score, which I'm going to talk about in a second. And then it's going to be times that margin of error. Okay, so this is the point estimate. This is obtained from the sample. Obtained from sample. This is the z-score based on the confidence level. Okay, and then this whole piece here is the margin of error. Okay, so number one, let's talk about we kind of talked about the point estimate. We know how to do that, right? We take a sample, number of successes out of the sample size, just fine, that's the proportion. How do we find the z-score? So there's a couple standard confidence intervals that we're going to be using. So instead of calculating those z-scores every single time, let's just jot down the z-scores that go with these sort of standard levels. And these are kind of like 3 standard confidence levels that we use: 90%, 95%, and 98%. And remember, the idea here is this curve, right? So if I wanted to know what is this z-score right here, right? What corresponds to this value? What corresponds to this value? Well, I'm going to go to my calculator, and I'm going to go to my distributions. And in this case, I'm not looking for a percentage, right? I'm looking for an actual value. So I want to go to inverse norm. And because our default calculators will always be talking about a full tail all the way to the left, I kind of have to know, all right, so this value right here has a z-score. This is the positive z-score, and this is the negative z-score. Okay? And so what is the area to the left of this? Well, if I just want to use the negative one, that's 0.025, right? So 0.025, and I'm on the standard normal curve. So I keep it as 0 and 1, and I hit enter. And we get something that rounds to about 1.96. Okay, so that's the negative side. If I do the positive side, it's the same value. Right? So what's the area to the curve to the left of this positive z-score? Well, that's 95 plus 2.5%, right? So that's actually 97.5%. So 0.975. And then we'll see the positive value of this exact same number. Okay? And so it doesn't really matter the positive or negative, because in our formula we have a plus and minus sign. So we don't really have to worry about that. So this number is going to be 1.96. So that's for a 95% confidence level. Right? 1.96 would be our z-score we use for 95%. For 90%, think about what we would do for that. So we would have a little curve here, and we'd be putting 90% in the middle. Right? So how would you find this z value right there? Well, what percent is to the left of this? 10% is not included, but there's 2 different sides, so that's 5%, right? So if I go back to my calculator, inverse norm, and do 0.05, we get approximately 1.64 for 90%. And for 98%, again, if we sort of sketch this, we got 98% here. So 2%'s left out. On one side is only 1%. And so we do that. And we get our z-score of approximately 2.33. Okay, so these would be the numbers we would be plugging in for the z value. Okay. Remember the p would be the p hat, and then q would be the other amount, and then we divide it by the n. So this margin of error is using the sample distribution idea of estimating the population proportion. Okay, so let's take a look at a full example. Let's see here. Okay. So, 800 randomly sampled 16 to 17-year-olds living in the U.S. were asked whether they have ever used their cell phone to text while driving. Of the 800 teenagers surveyed, 272 indicated that they text while driving. We want to create a 95% confidence interval for the proportion who text and drive. Okay, so what we have here is we have 272 out of 800. And so this is going to be our p hat. This is our point estimate. So what is 272 divided by 800? 0.34. Or 34%, right? Okay, so 34% say they text and drive. We don't know if that's the actual, right? That's just our point estimate. We're now going to create this confidence interval. Because we're doing a 95% confidence interval, we're going to take this 0.34, add and subtract, and we're going to do 95%. So we're going to do 1.96 times the square root of p, which in this case we're going to use the 0.34 to estimate, times q, right? So times what's the other percent. So if 34% say they do, what percent don't? And that would be 66%. So 0.66. Let me make that a little bit clearer. Divided by the sample size, which is 800. Make sure that this is all, I didn't do this very neatly. Make sure that's all inside the square root. Okay? And so, what we're going to do is, I like to sometimes first just figure out this value, and then I can add it and subtract it from 0.34. Or you can just type the whole thing in, do one of them with plus, type it all in again with a minus. Okay? So I'm just going to do this part first, 1.96 times the square root of 0.34 times 0.66 divided by 800. And I get this long decimal. So now I know it's going to be 0.34 plus and minus 0.0328 and so on. Right? It's good enough for rounding purposes. So I just do 0.34 minus this. So I like to actually do minus first, because when I'm going to talk about my range, I like to go from least to greatest. And so that's 30.7%. And then we're going to do the same thing and make it plus. So 0.34 plus that number. And that's going to be 37.3%. Okay, so that's the confidence interval we get. Okay, and so how we would write our answer here is that we're 95% confident. 95% confident. The proportion of 16 to 17-year-olds that text and drive is between 30.7% and 37.3%. Okay, that's how we're going to create these confidence intervals. So it's all about sort of using this formula here to create that confidence interval. Okay. The last part of this, well, first of all, a couple different things is notice as the confidence interval increases, right? As we go from 90% toward 98%, what happens to that z-score? That also increases. What's that actually doing to this confidence interval? Well, we're multiplying that z-score by something, so, and then we're adding and subtracting that. So that's actually widening the interval, right? And that kind of makes sense because if we're 98% confident, then we're going to need a larger interval compared to if we're only 90% confident. Okay. How about with sample size? Since we're dividing by the sample size, if in this margin of error, if we're increasing the sample size, think about what's happening to this value. If we're dividing by a larger and larger number, this margin of error value becomes smaller, which then means that the total amount we add and subtract becomes smaller, so our interval is smaller. And so we see that larger sample sizes will lead to smaller intervals, which again kind of makes sense, because if we went out and sampled 10,000 people, then yeah, we probably have a really good point estimate, right? So we don't need to go too much above that point estimate or too much below that point estimate to actually include the real percentage. Okay? And then the last thing the book talks about is how to find the sample size with a given margin of error. So suppose we wanted a specific margin of error. Like some people don't want a margin of error that's more than 5% or more than 3%, whatever it may be. That's all about just plugging into this little formula right here. So, for example, to find sample size, for a given margin of error, so in this case, we don't actually know any of the parameters yet, right? Because we haven't even taken our sample yet, so we don't even have a p-hat. So what we do is we just substitute 50% in, okay? Because in the book, let me get that out of the way. In the book, it talks about the different values for p-hat and q, right? For p and q. And the largest margin of error, so we want to kind of use the safest value, and that's going to be 0.5 because it gives us the largest value when we multiply, okay? Because 0.5 times 0.5 gives us the largest value we can get, right? 0.8 times 0.2 is going to give us something that's not as large, okay? So to do this, what we're going to do is we can use algebra to kind of solve the formula for n, and that's what the book has done for this example. So, or not example, just for the formula. So n, let me take example out. First, put the formula down. N equals 0.25 times the z-score that pertains to the confidence interval, just like the other thing we did, divided by, that's going to be our margin of error that we want, and then we squared. Okay, so for example, suppose we want let's do a 90% confidence level with, what's this book do? Within 2 percentage points. So it wants a margin of error of 2%. 2% margin of error. Okay, so what sample size would we need? So we would do n equals 0.25 times. So what's the z-score for 90% confidence levels? If I go back up, 90% confidence levels is 1.64. So I do 1.64 divided by the 2%. I'm going to put in as 0.02. And I'm going to square that. And then I just kind of type that into my calculator. So I'm going to do 0.25 parentheses 1.64 divided by 0.02 squared. And that's going to give me a sample size of 1,681. And so I would need to sample at least 1,681 people to get a margin of error of 2% on a 90% confidence interval. Okay? And that is that. So that's it for the first, for population proportions. Next time we're going to be talking about the mean, so getting averages, which is going to be very similar to what we just did, except, we'll be using something else in this place. We'll be using some other way of getting a margin of error. Okay, so in this place, right there. Okay. All right, so that was a little longer one. Hopefully next one it will be shorter. And I will see you for that one.